Excellent.
Okay, good. So, okay, thank you for coming. Today we are going to have the last tutorial from Dr. Ahmed. It's going to be on healthcare AI lessons from real world. Thank you for coming, and please.
All right, so thank you for the introduction. So in today's tutorial, I'll mainly focus on real-world examples, so some key insights from many of the use cases that I have actually worked on. So these are the systems which have actually been deployed, which have been used by hospital systems in the US and Singapore and other countries. And I will also try to minimize repetition with respect to some of the other use cases that I've talked about in earlier lectures and tutorials. All right, so I'll start off with the following lesson/premise that it's obvious, but it's also very easy to miss, that behind the data there's a real person which corresponds to the numbers. What do I mean by that? Especially if you're taking a machine learning and AI view of the data, and when you're building models, it's very easy to forget that the data that you have actually corresponds to real-world people. Okay, so I'll start with the first use case. So it's actually a project that I'm currently working on. It's with the Children's National Medical Center. So it's considered to be one of the leading hospital systems in the United States. So it's part of the work that I'm doing at Kensai. So we're working with Dr. Murray, who's considered to be a pioneer in the field. Okay. So the particular use case that we are addressing is that, so basically if you have pediatric ICU, so these are ICU or intensive care units specifically for children. Okay. And so the goal is to predict the patient's condition beforehand. So let's say predict 2 hours from now what the condition of the patient going to be. Is it going to deteriorate? Is it going to be stable? Is that person going to be in the ICU? If that child is not in the ICU, then is that going to be the case a few hours from now? So here's an example of the population that we consider. So basically these are children who for one reason or another end up in ICUs. And I believe that all of us can especially relate to not just the pain that this population, children have to go through, but also the pain of their families. So this is what I meant by real people behind the numbers. It's easy to forget, but well, that is the reality of the world. So this is basically so this is how we are defining at least one set of problems. So where the patient is, and the different states that they can be in at a given time. So they could be in ICUs, not ICU, or they can transition in between. And you want to predict their current and future states. So where this is useful is that it can be used for risk stratification, which is just another word for describing is that how much at risk the patient is. And so if the physician or the staff, if they know this beforehand, they can take some preemptive measures. So here's the data that we are using. So we have demographic data, we have information regarding medications, vitals. Vitals are things like, say, respiration rate, heart rate, so on and so forth, labs. So labs are basically things, so when you go to a hospital, they take some tests, they take out your blood, and then within the blood, depending on whatever condition that you have, they may do some tests, so that's labs. There's 4 terabytes of data, 1100 plus features, span 6 years. So an encounter is basically corresponds to, roughly corresponds to a person being admitted to a hospital, so 1.8 million encounters. And this is the distribution of the various states. So 70% of the states are within the ICU and a very small percentage corresponding to people being in transition. All right, so these are some of the results. Again, the exact numbers do not matter. So the x-axis basically corresponds to the different machine learning algorithms that we use. So, for example, LR is logistic regression. This is decision tree, random forest, extreme gradient boosting. The last two are deep learning models. So again, numbers don't matter. But there's one thing to note. So here we are predicting the current state, and here we are predicting the next state of the patient. So like in the next 6-hour window, and there are different versions of this. You can predict next 2-hour window, next 1-hour window, so on and so forth. So the main thing to note is, so the best results that we are getting are highlighted. So in this case, from random forest, from extreme gradient boosting, and LSTM and RNN, there are different deep learning models. And even if you don't know anything about machine learning, at least when you must have read news about AI in the news in medicine, then in general, these are the models that do best for a lot of use cases. So here, we are not getting the best results, but still they are pretty close. So we can make an argument regarding statistical significance. So now let's move over to predicting the future, the next state. So best results are from random forest, but if you look at RNN, LSTM is not added here, but the results are very similar. Okay, so here we actually observe that there is actually a wide difference in the performance. Okay. And then there's another 6-hour window, again, very similar results. Again, I'll emphasize the same thing. The numbers are less important. Okay, so what can we draw from that observation? So we are clearly here, we are dealing with large amounts of data. So 1.8 million encounters, 1,100 features, more than 4 terabytes of data. And in general, what we expect, or if you look at the literature, the expectation is that with deep learning models corresponding to more complex models, you should get the best performance. But that's not what we are seeing. Okay. Patient's condition. It's a complex problem to solve, but it turns out that to solve complex problems, you don't always need complex models. So that's an extremely important point. So just by using traditional machine learning methods, we are actually able to get better results. Okay. Because there is a tendency in literature, so for example, a lot of recent literature coming out in healthcare AI, even outside of it, that researchers basically using 1 or 2 models from deep learning, applying these models and saying that well, deep learning is suitable for these types of problems. That's not always true. You cannot make that claim until and unless you actually compare your results with more traditional machine learning methods. Okay, so why is that important? So a lot of organizations actually do not have access to large computing resources. So it may be that they can just run their code on, say, standard machines which are used, or even if they are using cloud, the computing capacity that they have available to themselves is limited, or their budgetary constraints. So basically, for a lot of so the main lesson that I want us to draw from that is that it is possible to solve complex problems by using traditional machine learning methods. In other words, don't bring a cannon to a knife fight. Okay, so now from that we switch gears and move on to more traditional use cases. Okay. Something that I've alluded multiple times, so improving an outcome does not really require that you focus on one thing. You may actually have to focus on multiple use cases to get some insights or to optimize things in a larger context. Okay. So here's an example where we worked with a large healthcare provider in the US. So it's like their customer base or patient base, 10 million plus members, 8 states and Washington, DC. And so here, what they are interested in is basically lowering the costs related to congestive heart failure. So the temptation being that, well, you map congestive heart failure to just predicting congestive heart failure. So it turns out that you can lower the cost even without building a model that predicts congestive heart failure, just by focusing on other optimizations that you can do within the system. So here are a few examples of what we focused on. So say just focusing on reducing the risk of readmission for those people, just focusing on how early can we predict end of life for those cases where we can, not just the machine learning model, but also the physician has a high enough confidence that they cannot do much about that person, because the resources are limited, and it's going to, and it may sound bad, but at a certain point, after a certain point in time, we just cannot do anything about the patient. And so if you continue spending resources on that particular patient, then that's also resources that can be used to save the lives of other people. So just by, in a hypothetical scenario, just by focusing on that, well, there's literally tens and thousands of quote-unquote saving in terms of days that one could do by redirecting those resources. And then on a more classical prediction level, we also identified a subset of patients who had a high risk even 5 years beforehand. So basically, for example, if you could predict somebody's at high risk of getting congestive heart failure 5 years from now, then you can start interventions which can reduce that risk. Again, for all of these use cases, the end result being that you have a healthier person and by extension a healthier population in the long run. Along with similar lines, so stitch-in time saves lines. Basically, scaling healthcare nationally. So I've talked about it multiple times, which is that the best type of healthcare is preventive healthcare. So focusing on use cases, focusing on things which can lead to better outcomes, or averting a crisis before it happens. Right, so for this project, KenSci, so we worked with are currently working with the government of Singapore. So the use case is basically reducing diabetes in the country. So they believe that, so the government has done some modeling, they believe that diabetes will be a problem for their population by mid-2030s. So they want to proactively identify people who are at high risk, have interventions, and basically nudge towards people healthier behavior. So basically we have created a risk prediction platform, and on top of that, a recommendation platform which makes recommendations from things from all the way from their food choices and physical activities that they can do. And people are incentivized and they're given rewards, virtual rewards that they can redeem. Okay, so what is the net effect? So this is based on just having this program for less than a year. That already the average patient activity has increased by 10,000 steps a day. And for this, I should mention that, so it's approximately like a quarter of Singapore's population have volunteered for this program. So and again, in the aggregate, this is a very good thing. So what does this translate to? That basically people are, say, walking more, eating healthier. Eating healthier, that's more difficult to quantify. But okay. So we just focus on this. Then in 5 years, the overall risk in the Singapore population is expected to be lower 3 times. Okay. So what have we done? So basically, trying to mitigate a problem before it happens. Okay. So a large number of use cases, problems within healthcare that I described can be formulated as supervised learning problems. So basically you have an outcome, you have a lot of data, and then you build an AI machine learning model with respect to that outcome. So it turns out that that need not be the case. Even using unsupervised models, you can actually do a lot. So this is another piece of work that we did with a healthcare system from the Midwest. So in this case, Michigan. So basically, they have 8 hospitals, 5,000 doctors, and 175K admissions. Okay, so here, so the cost of drugs is extremely high in the U.S. There's also a lot of wastage. Okay, so just by focusing on one thing, which is that, so using some different clustering methods to identify drugs which are prescribed together or substitute for one another. So think about the set of drugs which may be prescribed. So we're talking about tens and thousands of drugs. So you may know that some are generic, some are very specific. But if you have sufficient number of drugs, hundreds of thousands, then you cannot really do that analysis manually. Okay, so with this system, what we did was, so we automated that process, mainly using clustering. The machine learning methods basically finds cluster of medications also with respect to similar types of diagnosis, and then determines if there are things which are substitute of one another. So that's the automated part. And then basically we showed that that basically just using that you can have save more than $1 million. But there are other very interesting cost savings. So for example, that this particular health system could actually save $200,000 by just administrating certain drugs orally, that is, you take it by the mouth, versus injecting the same drug through an IV. Again, that's something that they were doing. And then the other thing is that you could actually they could save a large number of, like $500,000 just by simply changing the days of the week for certain types of medications. So now the question is, well, how do days of the week matter? So it just turns out that there are certain patterns that you observe that people taking medications are doing certain things on certain days, the beginning of the week or the end of the week, that the outcomes are better. All right, so another lesson is healthcare should be proactive. So what does that mean? So somewhat similar to the Singapore case. So we also work with the National Health System in Scotland. So the health system in Scotland, so that's also publicly funded, it's nationalized, and just within Scotland, so they're divided into 14 different regional boards, and 160,000 people who are working within that healthcare system. And so again, relatively speaking, a large section of their population is affected by COPD. So these are basically pulmonary diseases or diseases related to the lungs in one way or the other. And it turns out that a lot of them are at risk of readmission, which is basically that. So we have a patient who has a disease related to COPD. They go to the hospital, they get discharged, and it's highly likely that within, say, 30 days,